Hello everyone, I'll explain the solution to problem D, pairs of segments of Codeforces at around 150. So let's first look at the problem statement. Basically the problem says that you are given basically an array of some ranges. You are given a set of ranges and you need to remove some elements. So we need to remove some ranges so that the resulting sequence is a good sequence. So for example, if we are given ranges like this, maybe we delete this range, maybe we delete some this range, and then whatever elements are remaining, whatever ranges are remaining, they form a good sequence. Now, what is a good sequence? So the criteria for a good sequence are simple. The first thing is each range should be paired with some other range, and this should be paired exactly once. So for example, if we are given a sequence like this, then maybe 2 can be paired with 2 comma 8, but after that 2 cannot be paired with anything else. So it can be paired exactly once and it has to be paired, it cannot be left unpaired. Or and similarly goes for 2 8, since it's already paired with 2 comma 2. Now both of these are these are set, they cannot be paired with anything else. Second is you can only pair two segments if they intersect. So if there's a segment like this, another segment like this, like they're intersecting, you can pair them. But if the segments are like this and this, they are not overlapping or intersecting, you cannot pair them. You can pair overlapping segments as well because they are technically intersecting. So the pairs must be intersecting. And the third condition is that suppose we have um, some pair here Li comma Ri, and it is paired, it has to be paired with something. And there's some other pair of segments, suppose Lx comma Rx and Ly comma Ry. Then this should not intersect with any of these. Okay, so it needs to be disjoint. It will only intersect with this other pair with which it is mapped with. Okay, so for example, in this only in this array only, first of all, it's not a good sequence because the number of elements is odd, but let's ignore that. um, Suppose you made a pairing like 2 comma 2 with 2 comma 8 because they are two intersecting pairs, and another pairing that you made was 0 comma 0 with 5 comma 6. Let's assume you did something like that, and let's ignore this 1 comma 2 here for the moment. Uh, so we are fulfilling this condition, we are fulfilling this condition because these two are intersecting, these two are intersecting. But if you look at 2 comma 2 here, it is intersecting with the other ranges element, which is 0 comma 10, which is a bad thing. So this is not a good sequence. Okay, so this element should only intersect with the element which it range with which it is paired, and not intersect with any other range. Now uh, finally, initially you were given a series of ranges which may or may not be good, but you want to delete some elements so that later on it is good. Okay, so I think for this question only, if we let's say if we delete, which element should we delete? If it is enough to delete the fifth element. Okay, in this case we have to delete 3 elements. All right. Uh, so like, yeah, if you delete 5 comma 6 here, then we still have it won't still be a good sequence. So I think if you delete 5 comma 6, 0 comma 10 and 1 comma 2, then it's a good sequence. Or if you would have deleted, let's say 5 comma 6, 0 comma 10 or 2 comma 2, then you are only left with 2 elements, so that will be a good sequence. um, so now let's move on to the solution of the problem. I will first explain what I thought initially, and then why that will not work, and how you can move on from there. So I thought that, okay, we are given these ranges, right? Suppose we have a function which takes in some I comma j. That means that we are only concerned with the ranges from position I to position j. So we have like Li, Ri, and somewhere to Lj, Rj. And we are only concerned with this range, and we want to check how many elements we need to delete so that this range is a good range. Okay, now everything else we are ignoring, and eventually want to find the answer for function of 0 comma n minus 1 that will cover the entire range. I thought, okay, maybe we can think in this direction, and since the number of ranges is less than equal to 2000, then maybe we can reduce this to an order n square complexity, and we can go on from there. So I thought like, okay, what we could do is, um, if we are looking at this range from I to j, we can look at this ith element, Li, Ri, and then we can decide whether we should pair it with something or we should delete it. Okay. So we had some like function of I comma j, and if we choose to delete the ith element, then the total number of deletions would be 1 plus function of I plus 1j. Otherwise, we could pair it with something else. So we could pair it with, we have this element I, we have this j, we are looking at the ith range, and we could pair it with, something, maybe with the kth range. Okay, we could pair it with the kth range between I and j. But and then we could, maybe recursively solve for the remaining range. This was my initial thought process, and there are some problems with this. The first issue is that, suppose you pair, you are calling a function from I to j, which is a continuous range. And suppose you are pairing this ith element with something in the middle of this range. Now the new range which you have is from I plus 1 to k minus 1 and k plus 1 to j. You have to look at this complete range, right? This complete blue range. Like, you basically remove these two, and whatever is left, you merge that, and that will be a new range. And this is not continuous. So it will be difficult for us to solve it this way because your recursive function is taking a continuous range from I to j. The second issue which comes is, you need to maybe also remember what pairings you did before. For example, suppose you had a pairing from 2 comma, you had the ith element of 2 comma 8, and you had some jth element something, and you paired it with ith element, you paired it with something like, let's say, 6 comma 10. Okay, let's assume, and you paired it with this, and then you're recursively calling, or you have already done this pairing, you want to pair the rest of the elements, or you want to delete the rest of the elements, whatever it is. But suppose there is now an element in this range, let's say it is 5 comma 8. Okay, you have already paired these two, and suppose in the next iteration you are pairing this 5 comma 8 element with something else. You cannot do that because this 5 comma 8 will overlap with 6 comma 10, which was already paired. And we remember, this condition that an element, a range can only intersect with the range it is paired with and with no other range. So maybe we also need to worry about our previous pairing, because a new pair cannot intersect with any previous pair. So we also need to worry about previous pairings. So in the original solution which I thought of, obviously this is wrong. But I mean, it's not wrong. But why it is difficult is because you won't have continuous ranges, and you also need to worry about the previous pairings. So maybe we can modify this approach a little bit, and we basically need to overcome these two things. So uh, now have two conclusions. We basically want a solution where maybe we can maintain a continuous sequence, and we also don't want to worry about the previous pairings, because there can be many different previous pairings, and we don't want to worry about this. So we don't want to worry about this. So the way to do it now, and this will be the final solution, is we can maybe sort the sequence, we can sort the ranges. By sorting the ranges, we will have some constraints in the problem. We will be able to fix some things, and maybe we are able to overcome these two shortcomings. Okay, so I will now explain the actual solution. Suppose you sort the original sequence, and now you have a sorted range. So you have x1, y1, you have x2, y2, you have x3, y3, and so on and so forth. And now this is a sorted range, and this is sorted based on x. So sorted on x. Similarly, as to the previous solution, we will maintain a function from I to j, which will tell us um, how many elements we need to delete in the range from I to j in order for it to be a good sequence. And we want to find eventually function of 0, comma n minus 1. Okay. Suppose you have this range from I to j. So you have your elements like I plus 1, xi plus 2, y plus 2, and so on till x, j, and yj. We will look at the first element. Okay, now let's look at the first element. We have two choices. The first choice is we ignore it. So if we delete it, basically, so if we delete it, then um, when we delete it, we will basically call function of I plus 1 j, because this will be the new range which we want to capture, and we will add 1 because we have deleted one element. Now the new sequence, the new range is continuous, and we also don't need to worry about the previous element xi yi, because we have already deleted it and it will not intersect with anything else. The second thing we can do is we can either pair it. Okay, so what will we do is this xi yi will be paired with some element xk yk. Okay, all the elements between these two, since this is sorted based on x, right? This is sorted based on x. So this sequence is something like what I'm trying to say is that any range between these two, suppose xp yp, will always overlap or will always intersect with the combined range of these two elements. And the reason for that is, suppose we have this range from xi to yi. Okay, and then we have a range from xk to yk. The first thing is that since we are merging these two, xk cannot be greater than yi. So because if xk is greater than yi, so the two ranges will look something like this, and they are not overlapping. Okay, so, so either they can overlap like they will basically overlap either like this, or they will overlap like um, they will overlap like this. The I xk yi may fully also cover this element. Okay, so suppose the overlapping looks like this, then all the elements in this range will have their x value between xi and xk, because we are sorting on x. So they'll basically fall in the x will fall in this range and they will intersect. So we cannot take any of these elements in the future. We will have to delete all of them. That's what I'm trying to say. And if it looks something like this, then again the same thing will be there. All the elements will have their x coordinate between xi and um, xk. So their x coordinate will lie in this range, right? And no matter where their y coordinate lies, then since the x coordinate is lying here, which is overlapping with this complete range, we will again have to delete it. So what I'm trying to say is, this xi yi element, whenever it is paired with some other xk yk, and since it is sorted based on x, this xk will be greater than equal to xi. It's obvious that all the elements between them will be deleted. Okay, now that's the first thing. Now afterwards, when we are we have paired these two elements, we will there are also some other set of elements which we will have to delete. And why is that? um, Basically, the combined range when we are combining, suppose we are taking this example, and we are merging these two ranges. So this is how our combined range will look. Okay. So any element which has their x coordinate in this region, any element which has their x coordinate in this region will also be deleted because it will otherwise overlap with this entire range, and we cannot have that. So basically, there will be a set of elements in this range whose x coordinate is less than equal to this threshold, and that threshold will basically be max of yi and yk, because in for example, if these two are the ranges, this is how the ranges look like, then the maximum endpoint is yk. If this is how the two ranges look like, then the maximum endpoint is yi. So all the elements which have their x coordinate less than equal to yi and yk, they will also be deleted, and afterwards you will recursively call. So your call will look like function of ij is equals to, um, there will be some elements which are deleted plus function of I new and j. So you had this element xi by I, you paired it with some element xk yk. All elements in this range will be deleted. Some elements in this range, since it is sorted, right? So there will be a sequence of elements here whose x coordinate is less than equal to max of yi and yk. They will also be deleted, and afterward, suppose there is this element whose x coordinate is greater than this max of yi yk, then all the elements after it will also have the x coordinate greater than equal to yi yk, and we can just recursively call the function for this new range. Now, why will this work? Um, like we talked here, um, one second. We basically wanted to maintain continuous sequences, and we didn't want to worry about previous pairings. So this is now a new continuous sequence, and we also don't need to worry about this previous pairing, because of course it will not overlap with any pairing here, because all the elements x coordinate are greater than the maximum range of the maximum element in the combined range of these two elements. Okay. So this is how the solution will look like. And instead of having this function of I comma j, uh, this is like a recursive function. We will replace it with, we will use memoization, and we will replace it with a dynamic programming solution. So I will now finally write the final equation, and the final equation will be something like this: dp of ij is equals to, dp of ij means that you want to find the answer for this range from I to j. There are two cases. Either you ignore, you delete the ith element, and you make sure that it is unpaired, or you find some k. Okay, you find some k, and uh, basically you are pairing the ith element with some kth element. So how many elements are between this? Like I said, they will be deleted, so there will be k minus I minus 1, right? Plus there will also be some elements here, and basically it would be, suppose this is some index p. Basically xp is the maximum index, like p is the maximum index such that xp is less than equals to max of yi and yk, right? So um, it would be p minus k, and these elements will be p minus k plus dp of the remaining range will be from p plus 1 to j, and you want to basically find the minimum of this for all possible case. Okay, so this is how your dp solution will look like. These two will cancel out, and you can solve this in order n-q. For some reason it passes, but if you want an order n square uh, log n optimization, then what you can do is if you look at this equation carefully, um, uh, this thing, right? dp of also another thing is that you don't. This is a two-dimension dp vector, right? You don't really need the j value, because we will be calling we want to find the answer for dp of 0 n minus 1, right? Like I said, the formula will look like something like 1 plus dp of 1 n minus 1, and here also there will be some min k something something plus dp of p plus 1 n minus 1. So basically this n minus 1 will always be constant, because uh, if you want to find dp of 0 and minus 1, so this right range, this j doesn't really change, so you don't really need the second dimension. You can have a new definition of dp of I, meaning that you're looking at the range from I to n minus 1, and you want to um, basically find the answer for that range. Now I was talking about this optimization here, what you can do. So when you find, you look at this range, right? This can be this can be simplified to minus of I plus 1 plus dp of p plus 1. I'm assume I'm not taking the second dimension, plus p. So the dp of p plus 1 plus p is a function of p. So suppose um, you suppose p is 5, right? Suppose p is 5. So you would have at some point calculated dp of 6. So what you could do is, in your segment tree at the fifth index, uh, for p equals to 5, p plus 1 is equal to 6. So at the pth index, you can update a segment tree with the value of dp of uh, p plus 1 plus p. And then since this is the I plus 1 is common here, it is a function of I. So you just want to do a range query um, in the segment tree, and uh, you don't, because you want to find the minimum, so you can do a range minimum query in the segment tree from the index p plus 1 to n minus 1. And how do you find this p? P is, like I said, the first point, the first x, or the first index where the x coordinate is greater than equal to that threshold. So you can use binary search to again find it. So the complexity for the new solution will, I think, be something like order of um, n square uh, log square n, I think, because there's a log complexity for binary search and a log complexity for segment tree. And you can also optimize this, but it's good enough, and it passes the there's a 4-second time limit, so it passes it. The solution, I know it sounds a little bit complicated, but just to summarize, you are doing something like dp of I uh, is the answer for range from I to n minus 1. And then you have two choices here. Either you delete the ith element, so it will be 1 plus dp of I plus 1, or you pair the I plus 1 element with some k element, and you will iterate over possible k's. So you will find all the possible k's which intersect with the ith element, and all the elements in between that will be deleted. And then there will also be some other elements whose x coordinate is less than equal to max of yi and yk. So all those elements will also be deleted, because they will otherwise intersect if you take them. And then your solution will look like something like, I think, like you find that p index, so it boils down to this equation. Also, like I took p here to be the first index, the last index which was less than equal to maximum of y, yi and yk. If you want to simplify it, you can take p as the first index which is greater than uh, max of yi yk, and then the equation will boil down to um, dp of I is equals to minus I plus 1 plus, I think, p plus dp of p, something like this. So then you don't, because here this was p plus 1 and this was p, so it might be a little complicated. You can just move boil the entire thing down to um, the P index, and then you can store dp of p plus p in a segment tree, and then you can do a range minimum query there. Okay. I will also show you the code for this. I'll first show you the n cube complexity code. So I took this input array, I sorted it, and then we made this dp array. dp of n minus 1 I made it equal to 1 because obviously the last element cannot be paired with anything else from the range from n minus 1 to n minus 1. Uh, Otherwise, there are two possibilities. Either you delete the element or you find some j. Uh, I called it k in my question, but j is basically the range which you will pair yourself with. So if the two ranges do not overlap, that means array of j dot ff, that means its x coordinate is greater than the y coordinate of I, then they will not overlap. You can also break here. I just continued. Otherwise, these are the number of elements which will be deleted, and then we have to find the we basically have to find all those uh, k's. So we have to we have to delete some elements whose x coordinate was less than equal to the maximum of the two ranges which we are merging. So if there is an element whose x coordinate is less than that, so we will have to delete it. We will continue, and if we find some coordinate uh, which whose x coordinate doesn't overlap, so we can continue the dp function from there, and these will be the new elements which will be deleted. Okay. And from here, I looked at this equation and then I was like, how can we optimize it? So in this equation, d is this value, which is already fixed based on I and j. So we don't need to worry about that. This value is also fixed because of j. The only value is k plus dp of k, and we are basically filling the dp from right to left. So we already know the value of dp of k. So we can store k plus dp of k uh, in a segment tree, and that's what I did in the other solution. I uh, also this is n cube complexity because we are iterating k from j plus 1. So we can simply find the k by binary searching. So this is how I did it. I basically This is the same equation. If you look at it, max of array of j, max of array of. So we can just apply binary search to find the k, and then we can just query in the segment tree from the range of k to n minus 1, and we are updating the segment tree with dp of I plus I, uh, like dp of k plus k, right? So that's how we are updating it. So I know I might have complicated the solution a little bit, um, but I tried to be as thorough as possible. um, Thank you for watching the video. Bye bye.